Welcome to this lecture number 8 of the course Computational Hydraulics. We are in module number 2, numerical methods, and we will be covering unit number 4, which is ordinary differential equation and boundary value problem, or BVP. Learning objectives for this particular unit. At the end of this unit, students will be able to discretize ordinary differential equation along with boundary conditions. Also, students will be able to derive the algebraic form using discretized ODE and BCs. That means ordinary differential equation and boundary conditions. Ordinary differential equation with space discretization, we call it as boundary value problem, time or time like discretization, that is initial value problem. In our lecture number 7, we have covered this initial value problem. Physical problem in one dimension can be mathematically conceptualized using ordinary differential equation along with boundary conditions. Ordinary differential equation can be solved by using finite difference approach. Accuracy of the solution depends on discretization of ordinary differential equation and boundary conditions. This is specific to boundary value problems, but in case of initial value problem, we have seen that accuracy of the solution depends on the ordinary differential equation. Let us consider a physical problem. We have one water body on the left side, we have confined unconfined aquifer system, confined unconfined aquifer system with a leaky confining layer. This is impervious unit. So, in impervious unit is like mountain or any impervious rock strata present there. We have impervious bottom, and this is our groundwater table with yellow line, and on top we have ground surface. So, problem is we need to find out what is the variation of groundwater table with this direction. That means we are concerned about only one direction. On the left hand side, we have this water body, which is specified condition or Dirichlet kind of condition, specified head. On the right hand side, we have impervious condition, which is zero flux or zero Neumann condition. So, with this information, we can proceed and we can mathematically conceptualize the problem using differential equation and boundary conditions. So, mathematical conceptualization, we can write this differential equation where h is the head, which is a function of x only, and T is the aquifer transmissivity, C conf is the hydraulic conductivity divided by thickness of confining layer. This is related to confining unit, and HWT is the overlying water table elevation. So, this is our governing equation or G. Now, we need boundary conditions or BC. Left hand side, as I have discussed, we have Dirichlet boundary condition, x is equal to 0, we have HS or specified boundary. On the right hand side, we have impervious boundary or no flow boundary or Neumann boundary, which is dH by dx at L. L is the distance between the water body and the impervious unit. On the right hand side, this value is 0. So, we need to discretize the domain. So, we have some information. With that information, we can we have conceptualized the problem in terms of differential equation. Now, we need to discretize our physical domain with number of grids. So, let us say we are concerned about only x direction, that is why we are considering x naught to xn as grid points, and these are equally spaced and spacing size is delta x. Now, we can discretize our governing equation. On the left hand side, we have d2h by dx2. So, with that, if we discretize, this is our second order derivative, and second order derivative has got this second order accuracy. On the right hand side, we have c conv by t, and this h is basically h evaluated at hi, this is exact value, and hwt, this is a function of x, that is why this is again exact value. So, overall accuracy of the governing equation is second order. Now, we can discretize this equation and we can rearrange it. So, with h minus 1 term hi plus 1, we have rearranged it, and this is our right hand side term. So, basically these are coefficients. This governing equation is true for interior points. Interior point means that from point number 1 to n minus 1, excluding we are excluding the points 0 and n in this case. So, equation can be further simplified. We can write it in a compact form with these coefficients, where b is del x square, this di is minus c conv to del x square, ai which is again 1 by del x square, and ri which is on the right hand side as minus c conv t hwt xi. Now, let us discretize the boundary condition. Left hand boundary is Dirichlet boundary. Dirichlet boundary is without any truncation error. In general, equation format is B naught, because this is valid for our the first x naught point. So, if we use the general equation, that means the whatever we have used for our governing equation b, d, a naught and r naught, then we can write b naught is 0, d naught is 1, a naught is 0, r naught is specified value hs. So, if we consider a right boundary, then we can discretize it with backward difference. That is why h n minus h n minus 1 divided by del x plus first order accurate, this is first order accurate scheme. So, order of accuracy is del x. In general form equation, this is b n is minus 1 by del x, d n is 1 by del x, a n is 0, r n is 0. So, we have written algebraic equation for each of the interior points and boundary points. For interior points, we are using governing equation, and for boundary points, we are using boundary conditions in discretized form. So, if you see the algebraic form, then it is obvious that this portion is for interior points, and last two points are actually boundary points on the right hand side, which is impermeable boundary. On the left hand side, we have this d naught a naught, although a naught is 0 because this is specified boundary. So, d naught is 1 only, a naught is 0. So, in general structure, this coefficient matrix n plus 1 into n plus 1, and this h is n plus 1 into 1, and R n is n plus 1 into 1. So, solution can be obtained easily with this H equals to R matrix, R equation. H is A inverse R, and in this case we can easily get the solution, but the problem is the solution accuracy. We have discretized our governing equation with second order accuracy and our boundary condition, specifically right hand boundary, with first order accuracy. So, overall accuracy of the solution will be of first order. So, in tridiagonal form, we have boundary condition on top, then we have interior nodes, and at the end again we have this boundary nodes. So, it has got a sparse matrix structure. We have 0 values on both sides, and it has got minimum storage requirement. If we store this diagonal values, this is our B matrix, this is D matrix, D column vector, and this one is A. So, in this case A n is always 0, and in this case B 0 is always 0. So, considering these two external points or non physical points, we can construct the matrix, and we can store these values in individual column vectors. So, if we store the full matrix, the storage requirement is n plus 1 into n plus 1, but if we store it in column vectors, the storage requirement is 3 into n plus 1. So, obviously, we are gaining in terms of storage. So, obviously, computational cost will be reduced in this case. So, accuracy of boundary condition. If we use the second order discretization for first order derivative, then we can write this for right hand boundary with n, n minus 1 and n minus 2 points, and these are the coefficients. Now, we are getting one extra coefficient here, which is represented as E n 1 by 2 delta x. So, how to incorporate this within matrix structure? If we have algebraic form, so obviously, if you want to store the full matrix, this kind of arrangement is okay, but the problem is with this E n. E n is breaking the tridiagonal structure. So, this is increasing the storage requirement. However, we are getting second orders accurate solution. If you want to use a direct inversion approach, then we can store the full matrix and we can get the solution directly. However, in this case, due to this extra point, tridiagonal structure is broken. Although this is second order scheme, we need to preserve the matrix structure with second order accuracy. So, in first algebraic form, we have seen that the tridiagonal structure is intact. Second order accurate discretization of our right hand boundary condition, this is breaking the tridiagonal structure. Now, we can use governing equation for interior nodes. So, impermeable boundary treatment, we can create one fictitious point n plus 1 on the right hand side, where we have this impermeable boundary. So, zero Neumann boundary condition can be written as zero Neumann boundary condition can be written with our previous knowledge, that is center difference h n plus 1 minus h n minus 1 divided by 2 delta x. This is second order accurate. This implies that we have this value h n plus 1 equals to h n minus 1. Now, we can use this information in our governing equation. So, if we discretize the governing equation at node I, then we can write b n h n minus 1, this d n h n a n h n plus 1 and r n. So, for this one using the boundary condition, this can be written as, so in this case h n plus 1, in this case we can write it as h n minus 1. So, this can be simplified as b n plus a n as coefficient of h n minus 1 and d n, and these are the coefficients d n, a n and r n for the corresponding point x n. Again we are getting the algebraic form. We have second order accurate scheme because our governing equation is second order accurate. We are utilizing it for our boundary condition, and in this case tridiagonal structure is also intact. So, either we can use direct inversion or we can use spatial algorithm with tridiagonal matrix solution. So, matrix form, again we have two points and our tridiagonal structure is there. So, tridiagonal structure is preserved and completely second order scheme. So, at the same time we are getting two important points. One is computational, this will be better, at the same time the solution accuracy will be better. Thank you.